question 1. We're given a stochastic process x of t, which is a Whiteson stationary process, with autocorrelation r of tau and power spectral density s of omega. And show that first, autocorrelation is real and even. And we already know that autocorrelation is the expectation of two terms. X of t1 times the conjugate x of t2. And because x of t is a real process, that means the conjugate of x of t is equal to x of t. So we can just ignore this here. And so the conjugate of r of tau is pretty much we switch we find the conjugate of the x of t. So this term becomes conjugate of x of t plus tau. This term, we get rid of this conjugate. And we can swap the places here, and it becomes x conjugate t plus tau. And t1 minus t2 gives us minus tau. And so that we know r of tau is equal to r of minus tau. So the autocorrelation is even. And secondly, we're asked to show that S of omega is even and non-negative. So this is pretty much the definition of a power spectrum. If we replace the omega with minus omega, everything so we change the omega here because initially it should be minus j omega tau. Now we change it to j omega tau and replace the variable with lambda. Replace minus tau with lambda, and we have this pretty much. And this is a Fourier transform of autocorrelation of minus lambda. Yeah, and so and this term is basically just S of minus so because we know that autocorrelation function is an even function, so that r of minus lambda is equal to r of lambda. And so that this would become a Fourier transform of r of lambda, which is S of omega. And up until here, we've proved that S of minus omega is equal to S of omega, and therefore S of omega is even. And next, we'll use an example to prove that S of omega is non-negative. So imagine we have a system that is an ideal bandpass system where we keep the frequency content between omega 1 and omega 2, and the system function is 1 in this interval and 0 otherwise. So we can see that the output, the expectation of output squared, the square of the output would be this, and that is 1 over 2 pi integration of h of omega squared times s of omega d omega. And we'll have this. And because the expectation will always be, the expectation of something squared will also be no less than 0. And so we know that S of omega must be non-negative everywhere.